NMR is a very versatile technique. We can study structure, dynamics, interactions, so many different things, and we also collect many different types of data, or want to keep hold of many different types of data. So that could be spectra, peaks, chemical shifts, distance restraints, angular restraints, and all these many different types of data of course mean that we're using lots of different types of file formats. In addition to that, there are many different pieces of software. Usually these have been developed by academics across the world, and that's resulted in even more different file formats. The problem is that when we then try and convert between different file formats, we very often end up with data loss, and it doesn't always work particularly well. So a number of years ago, the NMR community came together to agree on a new universal format. There is a charter to this, the NMR exchange format, or NEF for short, and there is also a working group. And if you want to know a bit more about the background, have a look at this paper from 2015. Now lots of work has been going on in the years in the meantime to try and get this working and make programs compatible. You can see that a number of different programs are already working nicely. So CCPN, for instance, CS Rosetta, XPLOR-NIH, Amber and Yazara can both read NEF even though they don't write it, and also the PDB is accepting depositions in NEF format. In addition, Aria, now in its development version, is reading and writing NEF, and we'll show that to you today. Cyana has a slightly older specification of NEF implemented, so it does sort of work, but there are a few things that you sometimes need to change manually. And we'll also be showing you today NEF pipelines. Again, this is a program that's still in development, but we'll be making it available to you, and again that can read and write and do lots of things with NEF files. So the NMR exchange format is based on the STAR format, the so-called self-defining text archive and retrieval format. You're very possibly already familiar with it from NMR STAR files, and MMSIF files also use the STAR format. The nice thing is that within one single file you can cater for lots of different data types. It's also extendable, which means that different programs can add additional bits of data to it, and without breaking it for other programs. And finally, what's quite useful is that it's quite easily human readable, in contrast, for instance, to XML, which is a bit awkward for us to read. So this is the kind of structure. The file will always start with this keyword, so data underscore, and then it's divided into these so-called save frames. So you can see there we start with save underscore and finish with save underscore. Here we've got the next save frame and then another save frame. Tabularized data is saved in so-called loops. So this loop underscore shows the start of it, and then you have stop underscore to show the end. The table headers are shown to start with, and then we have the actual tabular data. And here you can see each save frame has a couple of pieces of metadata which always go along with it at the top, and then what comes below may vary. It could be more of these keywords, or it could be a loop. So within the NMR exchange format, it's been agreed on a certain amount of basic information which is mandatory in each save frame, but each software must be able to read that defined set of data, but any other data provided by other software packages can be ignored. So NEF is very flexible in that way and also extendable. And an example of that is here. So this is a save frame for a spectrum. And so there are some standard keywords here to show the number of dimensions, the chemical shift list that may be associated with it, the experiment classification, the experiment type. Of course, you can see here, for instance, you don't necessarily have to provide a chemical shift list, but you have the option to do so. And then what you have below is all of these keywords that start with CCPN underscore. And so these are CCPN specific things, and we use those so that if you save, for instance, a whole project as a NEF format file, you can in fact recreate your whole project. So here we're storing information you can see about contour colors, contour levels, scaling, spinning rate, all sorts of things. So it's up to other programs whether they want to use that information, otherwise it's just us. So if you want some more information on the Exchange, NMR Exchange format, then we've got a page here under our manual pages which explains some of what I've gone through just now. The more official page is this GitHub page, but it's probably slightly less user-friendly than what we've provided on our webpage. Here's a plan of what we're going to be doing in the workshop today. Different people are going to be running different parts of it. Have a look at those bits that you're interested in, and then for all of those there are tutorials available which you can then go through in your own time. So I'm going to show you how you can export and import NEF data within Analysis, and in particular how you can use that as a way to move data from one project to another. So we're going to start using the tutorial data provided with finding project_1, and we're going to open that here. And you'll see this contains here an HSQC spectrum of an apoprotein. And to export the data, we just go to File and then Export NEF file, or you can use the shortcut EX. So this is the dialog box. At the top are a few options. We're not going to include CCPN tags. So these CCPN tags basically enable you to save essentially a whole project as a NEF file, but we only want to transfer a few items. So this is what's actually contained within our project, in which the things that we can export. So we're going to deselect everything, and then we're going to select basically the chains. Here we want our chemical shift list, and we want this apo peak list, and we don't need the other items. So you can change your file name or your directory here if you wish, and then just click on export. So my file is here, but first I'm going to open the project where I want to import it. So you could close this project first, or you can just directly drag in the second project. And you can see here we've got an apo spectrum and also the one for the complex. So now we can either go to File, Import NEF file, and then select the file we want, or you can just go to your file browser, find your NEF file, and drag it into the project. You'll then be given the option to either import the file or use it to open as a new project. We're going to choose Import. So here we've got several sections to this pop-up. On the left-hand side, you can see everything that's contained within the NEF file which you might wish to import. If you want to look at any items, you can do so here by simply expanding these sections. And then on the right-hand side is where we organise how we want the data to be arranged in our new project. You can see that some of these things are shown in orange. That's because the names of these items actually clash with things that are already in our project. So we're going to have to change the names of these items before we can import them. So this is the chemical shift list. I'm going to rename that to APO because it's the chemical shift list of the APO protein. Make sure you press enter after typing in your new name, and you can see it's no longer orange and automatically it's been ticked to be included in the import. The peak list I'm just going to auto rename, and it changes this serial here, and again the orange has gone. If you wanted to add a comment, you could do that. And then finally, we select everything that we want to import. We also want to import the chain, so I'm just going to select everything here. Finally, click on Import. And then once it's done, we can see here, we've now got the original peak list that's actually just empty. And then this is the new imported peak list. You can see here we've now got the apochemical shift list, and under chains, our chain with the sequence has also been imported.
Okay, so I'm just going to show you a bit of a different way of using NEF files. So this is when we're doing NMR screening. So you might be screening, a particular protein target against a whole library of small molecule compounds. You start off by recording some control spectra, which will be recorded just on the mixtures of small molecule compounds, and then you would record the spectra where you've added your protein target as well. But then what you always need to do is compare those back to a set of reference spectra, which have all the information about which peak belongs to which compound, so that you can then work out which hits belong to which compounds and which compounds you want to follow up. Now, this information about these reference spectra, we actually recommend that you save in a NEF file, and you can then use that for the basis of each new time you do some screening. Now, you could say, well, why don't you just save it as a full CCPN project, because that's essentially sort of what we're doing. But the nice thing about the NEF files is, for a start, it's just a single file, rather than CCPN project is a whole big directory of files. Secondly, it's easily humanly readable and easily amendable. So if you want to change some file paths or something, you can just use find and replace. But at the same time, it still can contain a lot of information about our project. So we've got here a file, which I saved previously, and you can see it starts off just with some metadata. The molecular system would contain your protein sequence. Because we've actually not got a protein sequence in here, this is just the small molecule compounds, there is no sequence, so that's just left blank. And then you can see here we've now got information about spectra, and it will then also contain the peak lists. And alongside the first few tags, which are just the normal NEF tags, we've then got lots of information, and you can see that with these CCPN tags. So that's lots of additional information that we're saving here with the path, where the spectrum is saved, what color we want it to be, etc., etc. So you can see lots of additional information. Here's the peak list again with some additional CCPN tags. So we've got all the spectra are saved, and then further down we've got information about all our substances, all of the 200 chemicals that I'm screening against in this situation. So all I need to do is, as Eliza was showing earlier, drag it into the program. And you always ask, do you want to import it, or do you want to do a new project? So Eliza was showing how you import it. In this case, actually, we're just using it for the basis of our new screening project. So we just say new project. And it first of all pops up with a slightly unfriendly pop-up saying that it couldn't find my spectrum paths. And I need to go to the spectrum validate paths pop-up to sort this out. So that obviously is because my NEF file was perhaps, certainly this is going to be the case for you when you try this out, the NEF file was created on a different computer, the file paths for where the spectra are saved are different, so you will need to change those. So we go to spectrum, validate paths, and then we bring this, have this pop up, and it shows that all these paths here at the moment are incorrect, so that's why they're shown in red. And but you can see it uses this $data, which is this path up here. So all I need to do is amend this path to go to where I've got these reference mixtures stored. So I'm just going to copy that path, paste it into here, and Oh, no, that was too much. It can go away. And then once it's found these spectra, that all turns green. So I can now go to close, and then hopefully my spectra should be visible. So you can see here I've got these 10 spectra. If I open one, then we can see it in here. I've got all of these have also been placed into a spectrum group. I've got 10 samples, each of which contain 20 compounds. And here's my list of 200 compounds in my full screen. As well as having these spectra, I've also got peak lists that have been imported. You can see these up here. We've got annotations for our peaks. So for screening, we tend to put the annotations, not NMR atoms, but we have this annotation field in the peak list. So that's what I need to select here as my peak label in the spectrum display settings. And now you can see that I've got peak labels telling me what each of these compounds are. And you can even see here, I've got one that's been labeled as impurity. If I click on that and have a look at it in the peak table, you can see I've got this annotation, but it's also got a merit of 0. So that means when I get round to doing my screening, it won't actually include that. So there's a huge amount of information that's contained in that NEF file that's now been put into my project. I can now go to my screening data. This is all saved in an Excel file. It's basically got 3 different sheets showing the information on the control, target, and displacer samples that I have. I can just drag this in, hopefully, to the sidebar. There we go. And you can see now it's added in all my control, target, and displacer spectra, groups. And if I now try and overlay control 1, target 1, and displacer 1 with the ref mix 1, you can see these overlap nicely. I can also stack them. And here we can see that's worked nicely. And I'm really set to do my screening and work out whether I've got any hits or not. So I'm not going to show you how to create one of these NEF files. There is a tutorial which will show you that. If you want to talk about that more later, then I'm happy to do that.
My name is Gary Thompson. I'm a facility manager at the University of Kent, so an NMR facility manager. I'm also a co-I on the CCPN grant and a member of the working group. And what I'm going to talk to you today is about some software I've been writing, which is not part of CCPN, but it's very much related to using NEF. So it's a piece of software called NEF Pipelines. As the image may suggest, it's designed to be a bit of a Swiss Army knife of tools to work with NEF files. NEF files are reasonably complicated and structured inside. I don't know whether Eliza's done her warning already about whether you should or shouldn't edit NEF files, but to get them right, there's quite a lot you have to do. So this set of tools is designed to help you. It's designed as a set of simple tools written in Python. And these are examples of the sort of tools that's in there. There's really 2 sets of tools. There's one set of tools which is for manipulating NEF files and things like translate and header and listing the chains in there and streaming NEF files into a pipeline. And we'll talk about what pipelines are in a minute. And then there's a set of foreign file access tools. Excuse me, I have a cough at the moment. It's not COVID, but it's rather ticklish. So this will do things like read and write NMR pipe files, not data files in the sense of spectral data, but things like metadata. So NMR pipe peaks, for example, NMR pipe shifts, and the same with NMR view. The idea is that these tools are there for things where you don't have NEF support in the programs at the moment. Indeed, it'd be lovely if in the end, if some of these got retired, but it's going to take quite a long time because there's a lot of software out there that isn't NEF ready at the moment, and this is to help you with that. And there's always going to be a need to read older projects and things like that. To give you an example of one of these tools, they're hierarchical. So there's a tool called Frames, which lists the data frames inside, or it can list the data frames inside a NEF file. So these are the chunks of things we store things in. So there'll be like one data frame for molecular structures, another set of data frames for chemical shifts. And this command can do things like delete them, insert frames from an outside file into another file, pretty print frames, so on and so forth. How do we get to it? It's run as a command line. Excuse that a moment. It's run as a command line, and this is what you'd have to see if you just type NEF on its own, and we'll see this in the exercise. You can type NEF help, or you can type any of the subcommands with help. These are the top level subcommands, and you do lists of subcommands to get to lower level parts of the program. It's quite hierarchical. We'll show you that in the demo. So what's a pipeline? A pipeline is a small, well, a part of a pipeline is a small, in our case, Unix tool, which has a very simple defined job to do. It has an input, an output, and it will tell you errors as well. We can build up what we do with pipelines by connecting them together, however. This is very much the Unix tool philosophy, and maybe familiar to people who've used NMR pipe as well. So here we have something that's reading a FASTA file, and then once it's read the FASTA file, we go to NMR pipe and we read in some peaks, and then we produce a NEF file out the end by saving it. Okay? Or once we've got the NEF file, we can pass that to something like CCPN analysis. But we could do something else. We could save it to a file, and then we could actually come back and take an NMR-FX pipeline and write peaks for NMR-FX and write those out to an XPK file, which we then put into NMR-FX or NMR-View. Okay, so that's the simple idea of a pipeline. The whole idea is that you collect the output of one command, the input of another command, and then if you need to into a file, we could actually eliminate this file here. We could actually take the output of the pipe peak writer and put it into the NMR-FX peak output directly. So what I'm going to do now is run a little demo of using NEF pipelines. This is the usual thing with demos. You never work with children, animals, or fresh software, but hopefully this will work well. This is data that's in the data that we've provided with the tutorials here, and there'll be a tutorial on this. It's data from a protein called SEC5. And the first thing we're going to do is just stream the data file onto screen. And we can do that by doing NEF stream sec5.nef. Yeah. Okay. Oh dear. That's a problem. Why has that disappeared? I have some problems. I told you there would be.
It was working earlier when you showed us.
No, I think it's because I've rebuilt. Give me 2 seconds. Sorry about this, folks.
So we should perhaps add that in order to install this, we've actually now on the update server as part of analysis, we've got a script in there which will allow you to install it.
Aha, I'm back in working order again. So this is showing that if you type NEF without input that it understands, it will show the help screen. We can also do -- help as well. And that will produce this screen. So if we do NEF stream sec5.nef, that's just going to stream the NEF file onto your screen, because the output of the stream command is connected to your terminal. But what we actually want to do is we want to actually export to a program called MARS, which is an automated assignment program. So this NEF file contains data for a small protein and includes chemical shifts from triple resonance data that we want to assign. So we can do NEF MARS export sequence, because the first thing it needs is a sequence. And if I run that, we'll get a couple of warning messages. These are to do with the version of software we've got. These will disappear in the next version. And nothing else appears to have happened, because this is the way Unix tools are supposed to work. If you actually look in the directory, we now have an extra file called sec5 part 2 faster. And if I more that, you'll see that's a faster file that contains the sequence that wants to go into MARS. The next thing we want is some shifts, so we can do NEF MARS export shifts, and that will run as well. And again, if we ls, we'll now find that we've got a shifts table as well. We'd also like an input file for MARS set up. So we'll run next MARS export input. And we'll now find that we have 5 files, including this file on screen called .input, sec5, etc. .input, which is the input for running MARS. And it has all the names of the shift files and the other files that you need set up already in it. The only thing I don't like here is the long file name we have here, which is a bit wordy and really doesn't have what I want in it. This is taken from the name of the entry in the NEF file. If I actually go back to and run the stream again and look at the start of the file, it's this part of the NEF file, which defines what all the data is kept in. And I'd like to have a much simpler name for my files. So I'm going to put an extra command at the front of the pipeline, which is going to be NEF entry, rename, and we call it sec5 run 1, for example. And we need a pipe symbol in here. So each of these subcommands is separated by a pipe. So NEF stream is producing this text, passing it to NEF entry, which renames the entry, and then it's passing it to the export commands. If I run that again now, you'll see we have some sec5 run 1 files, and these are the renamed ones. This has only been renamed in memory. It's not been renamed on disk. The final thing you might want to do is you might want to record this as a script we can run again. So let's put it into a file. So we'll export to Mars. .shell. We will remove the sec5 part 2 files. And we also remove the sec5 run 1 files. We're back to where we were at the start. If we source export to mars.shell, that will run again, and we'll reproduce all our data that we had earlier. So we have a reproducible data flow. And if I want to come back and see exactly how I manipulated the file and what I did to get my Mars input 2 years later at the end of my PhD, or when I want to write a paper, it's all here. Okay, and that's a very swift outline of how to use NEF pipelines. There's quite a lot more things you can do with it. It's still being developed. It's available as an exercise this afternoon you can run. Thank you very much.
Okay, so now from a bit of more hardcore to lightcore. This part has been quite controversial for our group in terms of it's not something we recommend you do on the whole. The reason why we've decided to include it is because we had few users who essentially sent us a piece of some old kind of file with chemical shifts or peak occasionally, and it was in tabular form, and asked us, can I possibly put it in the project? So I mean, yes, you can. It does require a bit of a moving columns and creating text files and things like that. But as a last case scenario, you can. Please don't do it ever for NMR star, because we have a dedicated importer for that. Do not use it for any deposition or anything of the sort. And it is a little bit time consuming, not very difficult once you get started, but yes. Herten is strongly against ever using this tool, but it is a last case scenario. So just to get started, this is an example of chemical shifts that I was given by a user, and so I really would like to have it in the project. I have a sequence for it. I was like, okay, fine, because as you see, there are fairly visible columns, so it's tabulated, and if it's tabulated, you can turn it into a loop into in the NEF file. So in this example, we provided a template NEF file, which is the most basic as you can possibly have it. So it's the metadata, and here the program name is my invented. Well, it's essentially just me making this file, and just to you can change the UUID into whatever random unique name you have. However, it's not really that important if you just keep it for yourself and not doing anything else with it. So as we said earlier, there is molecular system with sequence, and then there is chemical shift list in which we're going to input essentially that data in. So from a fancy command line NEF pipelines, we're going to go to something very basic, which is just Excel. So we can just copy that data from this file, and again we've included the Excel spreadsheet that I just use on occasions where I have this problem, and you can import this text file straight into the Excel via the text import wizard that opens this kind of pop-up. Importantly, it's important not to include any dot as a separator for the columns, because, well, we don't want to have our chemical shift split. And as you see, all the data has been nicely split into the columns. We have our residues, a sequence, chemical shift values, so we can just finish with that. So now we have it in Excel. Now how we can put it into our template. Here are the number of, or rather, column headers that we must include in our chemical shift loop. all of those values are mandatory, so they have to be there apart from maybe value uncertainty. But since we have it in our data set, we might as well just include it as well. So we have our value uncertainty in here in the columns J and K. We don't have chain code, so we will add that. We have sequence code, which is in either column D or E, and we have our atom residue name and atom name, which are an F and G. So we pretty much have almost everything we need. We don't need those two columns. Excuse me, you can just remove them and just add an extra column to incorporate the chain code for our into our NEF file. Because I've done it a fair number of times, I have my column prepared, and I can just paste it for this data set. And now I have pretty much everything I need to create this this loop with the chemical shifts. So now all I need to do is just copy this section from the Excel spreadsheet and paste it here in my NEF file. Now, important thing to make sure of is that the order of those columns that we have here is reflected in the names of the column headers that we have under the keyword loop. So as you can see here, the chain code, yes, it's in the correct position, but shift value uncertainty is actually on the far away column. So we want to move the sequence code, residue name, and atom name higher up in our list. So now chain code is in the first position, sequence code is in the second, that residue name, atom name is here, and now we have value and value uncertainty. So the column headers reflect the column order in that loop. So that part is done. Now we have to make sure we have our molecular system as well in here. The user sent me also the sequence of that section. So now it's conveniently was already in one column. If you don't have it, you can easily convert it. There are lots of tools available online to make it like that. So the easiest way, again, I have my template ready because I've done it a number of times, and I just copy it here. Looking back at our template, I have my index now, which will be column A. I have my chain code, which is B, residue names, which is C, and now only I need sequence code, and just copy that section here, and there you go. All I need is here. I'll just paste it into appropriate place, and everything follows the right order that I have here. So important thing to remember in loops, it doesn't matter which column goes where, as long as the name of the column headers are in the correct order. So that's done. This is done. We also included in this template file part for a spectra. I am not going to show it because obviously the number of column headers is much greater, and it's much more time consuming, but it follows essentially the same rule. You divide it into columns, you make sure that the columns are correctly represented in this order, and that's pretty much all you need to do. I don't need it here, so I can just remove it. I can save it as something new NEF. And that is good to be imported into the project. So let's just test it. And here's my new NEF. I can just drop it onto the drop area. And again, I want to just import it, select it all, import. And there you go. I have my shifts and I have my chain, but shifts that I was after. So whatever NEF pipelines are not capable of doing for you, you can do with this simple way. You don't need obviously any programming experience for that, or a slightly scary command line. And you can have your shifts if you can divide it into columns. But as I said, and as I promised to Herten, I will emphasize, don't do it if you have any other option of not doing. The next section we wanted to show you is really how we use NEF file to really move information easily between various other software packages. And that's particularly important with structural calculations. So that is just a brief overview of the workflow that we use in the structural calculation. We had to use a lot. So we prepare our chemical shifts, our peaks, and our software and CCPN project. Once that's done, we export NEF file. This NEF file, the same NEF file, can be used by various packages, and Benjamin will show you how to do it in Aria Web. And I will show you how to set it up in XPLOR-NIH. Once XPLOR is done with its calculation and comes up with the restraints and the structure, restraints are then are written in NEF format. Those can be then easily imported back into CCPN analysis and grouped and inspected. And the same NEF file, together with the structure that has been produced by the calculation engine, can be used to validate in the wwPDB website. So in principle, and really in practice, it's actually quite easy and streamlined process. The only thing that does not involve directly NEF is really importing the results of the structure of the validation back into CCPN. We have a separate dialog, separate function that will do it, because unfortunately they produce XML rather than NEF file. But apart from that, everything is NEF based.
So basically, how the NEF file are supported in Aria or our new web server, Aria Web, is very similar to what was done in its version 2 of CCPN. Basically, you could import data from a CCPN project and be exported to a CCPN project. This was V2. Now with version 3 of CCPN analysis and so on, we are using NEF to pass the data between the two software. So it's very similar to what we had. So basically the user selects which type of data he wants to import from the NEF file into Aria, and everything that has been created by Aria, so all the restraints, all the assignment of the cross peaks are exported back to NEF, as Eliza mentioned, and also with the coordinates of the structures that have been produced by Aria, are in LMC format. We try to fix this share very quickly. And yeah, so then, and this NEF file and LMC file can be then used for deposition at the PDB. For people that have been using the standalone version of Aria with our general user interface, this is basically how it looks like. You have a new entry, which is the NEF input file. And then you have a new format that is accessible, which is NEF. And then you have to select which part of the NEF file you want to use. So here for the chemical shift list, you just click select NEF data, and then a pop-up window will show you all the corresponding chemical shift lists. that are available, and then you click OK for the one that you want to use for this this spectrum. So basically, Aria can import definition of the sequence, chemical shifts, the peak lists, and any type of restraints such as dihedral angle restraints, adjoint bond, RDC, or also distance restraints that are present in the NEF file can be imported into Aria. And in the end, Aria also exports back new NEF files containing the input data and what has been added by Aria, such as the assignment of the NOE cross-peaks and the restraints that are generated. And the file, the output NEF file, is basically in two flavors. One that is like minimalistic, the one that you can use for deposition, and a more complete one where we add additional data such as a list of violations, restraints that have not been used for calculations, and stuff like this that can be read back by a CCPN analysis, maybe for a further inspection of the results. And so basically the support of NEF, it's close to be finished, but it's still in development. And I have to thank Vicky, Eliza, and all the NEF work group that gave us a lot of feedback and help to have this included in Aria. And so basically it's available on our development server, this Aria Web Dev. And if someone is interested, we have also a standalone version that is available, that has to be installed on your computer and that you can use locally. Now, what I can do is show you a small demo on how you can use this NEF file on our Aria Web server for structure calculation. So this is how the server looks like. So if you have an account, you can already log in. If you don't have an account, you can register, or you can even use it without registration. But then you have to keep in mind that the data might not be saved, and you maybe not be able to retrieve the calculation you add, because it's based on the session of your browser. So if the session is closed, you will lose all what you've done on the website. So anyway, for the demo, I can do this. So then it's basically the home page. What I want to do is to create a new project. I can give it the name like demo. And this is what we had before. You could import a whole old CCPN version 2 project, or you can import an NEF file. So here, just hit browse, and I will use this input new NEF file that has been provided by the CCPN team. And basically, once you have put this, you click save. So this will create your project, and Aria Web will look into the NEF file to know which data could be used. And then we want to perform structure calculation. So we click new structure calculation. This is basically, maybe call it a run 1. Maybe I can make this a bit larger. Yeah. And then we have a next button. So you will see that often on the website. So basically it tells you, so go to the next step where I can input data or parameters. Next, then this is very similar. This part on the left is very similar to what we have in the user interface of Aria for the standalone version. Basically, it defines all the input data. So we start with the molecular system. We see that NEF format is already selected, and the entry in the NEF file is called NEF molecular system. So it's already selected. Then we click next, and now it's about the spectra or the peak lists. And here for the chemical shift list, we have to select format NEF. And then for the NEF name, we'll see what's provided from the NEF file. We only have one chemical shift list. Now for the list of cross peaks, NOE cross peaks, again, NEF format and for the name. So here there are two spectra, so the N15 and C13 NOSI. So we just select one, and we can add second spectrum. And again, NEF, the same chemical shift list. Again, NEF format. And so we took before the N15, now we take the C13. We can click next. Now it's about the protocol for Aria. We'll use all the default values. Next again, about the simulated annealing, so how the structure calculation will be performed. Again, default values, we click save. And now we have our project here, and we can just click the start Aria job, and then it will send the calculation remotely on the computer cluster. So we do this, and we see now that our project is building, data are uploading, and now we would just have to wait to see the results. So it can take like maybe between 30 minutes to hours, depending on the parameters. And the good thing is that I've already performed this calculation, and I can show you how the results look like. Just need to find the link. Would be, yeah, here. So basically, when your calculation is finished, this is how you can visualize the results in Aria Web. So this is a structure ensemble that we obtain, and there are some statistics of how many restraints were used, how many restraints are still violated, how many restraints were merged, how the RMSD of the ensemble evolved along the different iterations. We have also some indication of the quality of the structures, like definition of Ramachandran parameters, the values from what if or what check, also from mole probability. And there are some additional results, like this summary table. So it's recapitulating all the statistics about your calculation, and it's very similar to the table you see usually when NMR structure is published. You have all these values that are presented, number of restraints, violation of restraints, deviation from ideal geometry, and so on, and the RMSD of the final ensemble. And what you get also, it's a way to download the complete Aria calculation as you would have for the standalone version. So once you download this, you end up with this run1 directory. And here you have the structure files. You see for structure folder, you see for all the iterations. So we are interested in the last iteration. And then here we can find our two NEF files that contain the output from the Aria calculation. And I wanted to show you what's different between the two, basically. So here on the left, we have the input that we use. So we use the molecular system, chemical shifts, the two peak lists for N15 NOSI and C13 NOSI. And there was also a diagonal angle restraint list that I forgot to mention. In the simple NEF output from Aria, we still have the molecular system, the chemical shift list. We also have all the distance restraints that were used for structure calculation, and the other restraints that were used for structure calculation that were not altered by Aria, but simply used as is during the calculation. In the more complete file, we also export the initial list of cross peaks, but with the assignment that were made by Aria. Also a list of distance restraints that were not used because they couldn't be fulfilled along the different iteration. Also this peak restraint links. So basically it tells you which peaks corresponds to which restraints, so either used or not used. And also we have our own nomenclature for one frame that lists all the violations that are still present at the end of the calculation.
In the case of XPLOR-NIH, in case you've ever used it, doesn't have a web interface, and it's very script-based piece of software. So we kind of built a little bit of a package or dialog box around it to make sure you can easily use it. So I will only focus on parts of our structural or solving structures from NMR data tutorial, which strictly involve NEF. So those, I'll go through those points. But if you're interested in, you can follow all of it, and you can try to download as well Aria results and follow the same steps in trying to put that in into the tutorial projects. So for this part, we will use analysis structure, not analysis assign, because we will need all those, or if you follow the whole tutorials, you will need the elements from that particular menu. So skipping the whole part of chemical shift preparation and peaks, we will go straight into the structure _2 project, which has all this stuff prepared already. And to set up the structure calculation XPLOR, we go to structure menu, go to setup XPLOR-NIH structure calculation, and you will see this pop up. It's going to be run 1. In this case, I don't have any, or I don't want to use the CCPN CPU more than 1. And in general, those are very intensive calculations. So if you have any access to multi-core processor, then I would strongly recommend using it. Because there's only one chain in this project, it's going to be automatically included. I want to include both my nosy lists, carbon and nitrogen, and the chemical shift list will be included for that spectra. So essentially, underhood is also an NEF importer. It's just a little bit more simplified, and it also creates an appropriate folder on your disk and copies all the scripts from excuse me, from XPLOR directory. The XPLOR directory is already set up in your preferences. Again, the details are in our structured tutorials. And see, once I press setup, we get a pop-up window informing the folder has been set up, and run the script in that directory. So can close that. We can have a look that in our structure folder in data, there is XPLOR-NIH folder, and the appropriate folder has been set up with our input file, input NEF file, which has all the information that we wanted to include, sequence, chemical shifts, and peaks. And we have scripts that you just have to run in terminal, and we'll go through your calculations. That takes a long time. So obviously we've prepared ready-made results, similar to Benjamin, in XPLOR-NIH done. This is the run 1 that I've prepared. And in here we have the out.NEF, which apart from what we have given it, so sequence, chemical shifts, peaks, it will also have restraints and links that will bind, that will link the peaks from which they originated to the restraints. It also has loads of comments, but they are ignored by software. So we don't have to worry about that. To analyze that, all we need to do is essentially drop this out.nef into our drop area. We want to add information from that nef, not new project. So we click import, and after a while we have our pop-up window. And here, as I mentioned before, there is a field to examine the incoming nef information. Can verify we already have chain, shifts, and pick lists. So we're not really interested in those, but we are interested in our restraints and restraint links. But before I start with importing it, for instance, we can have a look. There's this one. If you're not sure, oh, what could that be? You can just click on it, and you can use those fields here to examine what is that. Those are the dihedral angle restraints. So maybe in one of the first steps, I actually would like to rename that dihedral angles to roll, right? Remember to press enter to confirm the change. That has updated. And in this case, because we're importing results of structure calculation, those fields are on the right-hand side become much more useful. Actually, the dihedral, I probably want to separate into different structured data. Structured data are the data items that we use in our project to organize the data. And I just want to have dihedral as a separate structured data, but I still would like to put them in one collection. So here, what is collection? Collection is another data item that we will use in our project. You can think of it as essentially a bag to which you can put whatever you want for whatever reason. And in structure calculation, that becomes very useful because we can collect everything that, for instance, comes from one run, from run number one into this bag. So we can organize it, but we can also use that collection for driving certain analysis. So I'll just prepare myself a collection, run one, and as I press enter, that's automatically added to. I apologize, to this collection. So now I can focus on my distance restraints. Again, if you're not certain, oh, what that is, you can have a look in those fields. Those ones I will want to put in separate structured data and run one XPLOR, but I want to include them still in run one. And remember always to press enter, and this collection was already available, so I could just scroll down and select it. And as you see, whenever I modified it, whenever I changed the name, it has been automatically ticked because so far now I'm interested in it, and the restraint links are going to be ticked as well. So that's all done and ready. You can just click import, and here is what I get. You can inspect here my structured data with my run one underscore XPLOR, and here are my dihedral, and here are my collections, which you can expect to have all those elements in it. During the structure calculation, or rather after XPLOR returns the structure calculation, the folder that you will receive will have everything in one. It's not going to be organized in any way. So as a part of it, and there are detailed instructions inside the tutorials, you can essentially organize this in that way. So we put everything in the correct folders. Aria kind of does it by itself. But one of parts that, or in addition to sorting everything, all the files into the correct directories, we also create violations in the NEF format. That's a script that has been written by Gary, and this essentially just harvests information from XPLOR and just converts it into the NEF. Thanks to which we can also just drop this violation underscore for NEF file. Again, we want to import it into our project, and here those are very large files, very detailed, because they contain each violation or each restraint is analyzed per model. So as detailed as you can get for violations. In here, it's very important to make sure that this those violations end up in the correct structured data, because that is the way how we link the appropriate restraint tables with the appropriate violation tables. So can find the data straight, the structured data, and select them in this pop-up. But again, I want to have everything in one collection just to keep it all together. So I also select, please put that reference to that collection. And you click import, and you will see the violations, violation tables ended up in the correct structured data, and they are ready to be further processed and used. And again, details are in the tutorials. But one more detail which we wanted to mention is that you can use the same NEF, the out NEF that has been produced, or the NEF from Aria, to validate your structure at the wwPDB website. So it's this kind of a form you need to fill in. In future, we have plans to streamline it far more, but at the moment you do have to go through this form to fill it in. Obviously, I have prepared the session before. You normally get an email with the number of your session and the password that you have chosen. So once that loads in, you choose the file, and I am interested in my run from structure 2, my XPLOR-NIH, and I choose this out.nef. Right, you have to then select what is that, what file is it, and you also need to upload your model. At the moment, it's in PDB, but Aria will produce MMCF. So I'll select and run it. That takes about an hour. So we've done it ahead, and the result of this validation is prepared in either PDF. It's a quite detailed report, so a lot of information is there, and extremely large tables. They also produce the XML version of this report, which we can then load via a special dialog, which is in the structure menu, structure, import wwPDB data. Here you have to select appropriate file that you've just uploaded and saved. I'm really sorry, my phone is really not helping at the moment. Once you open the file, the report itself has a wealth of information. So it will also include the violations on your restraints, and that is one of the great advantages of using NEF, because now everything is standardized and you do get a reliable validation of your structure. So here we have a few options. We can import the violations, we can import the Ramachandran plot and Rutemeric data. You can change the names if you want to. The only thing is that you have to select which structured data the violation table should go into. Just a word of caution, at the moment, we don't have full functionality on the table that is going to be created from that report in comparison to what we can already do with the violations imported from NEF, but that is coming. We are waiting for the PDB to update their XML report. So as you see, this violation table has been added to the same structured data and can be viewed and analyzed. So that is it when it comes to use of the NEF in our structure calculation workflow.